With every breath, I breathe in so much of inspiration. I feel if there is one thing as free and as important as oxygen, it's inspiration. Hello students, so welcome to this topic called carbonyl compounds, aldehyde and ketones. So let me do a very simple introduction of these two compounds, aldehyde and ketones. For the aldehyde, in short we call them RCHO, where R represents the alkyl group and ketones will be R2CO. They are among the widely occurring compounds in all the organisms, and it is required by all living organisms, and we can find them in the solvents and as a starting materials in the chemical industry. One of the basic carbonyl compounds that you ought to know will be the formaldehyde, where they use it to preserve the carcasses, and in funerals, and for acetone, for the ladies or any of us who puts makeup or polish our nails, this is the turpentine to remove the varnish. You can find these also in coenzymes in the body and in steroids, in hydrocortisone, some kind of topical drugs that you could apply onto yourself, these creams. So for the formula, HCHO, this is one of the simplest form of the aldehyde. It's called formaldehyde, and the systematic name will be methanol. Acetaldehyde, ethanol. Acrolein, common name, propanol. So you understand that all the aldehyde ends with the L. Right, you change the alkane name, which ends with the E, to L. Ethanol, propanol, 2-ethyl-4-methylpentanol. So because here the highest priority group is an aldehyde group, so this must be carbon number 1. It has to be. Then you just count this way down and see what are the substituents. For the ketones, we replace the terminal E with a corresponding one, not 1. So this is called hexane 3-one, don't say hexane 3-1. This is hex 4-ene-2-none because primary functional group here in this molecule is a ketone. Ketone trumps your alkene. So this number must be the smallest. So we count from right hand side 1, 2, 3, 4, 5. Between the carbon number 4 and the 5 we have alkene. Carbon number 2 we have got the ketone. So hex 4-ene-2-one. This is hexane 2,4-dione. Now if there's another functional group that beats this ketone and aldehyde, then we treat this as a substituent. So we call this, you can pronounce it as acyl or acyl. I like to call it acyl. The acyl group that ends with YL, like acyl, acetyl, or acetal, formal, and benzoyl. Recognize these parts. Now revision from the previous lectures, we learned that when we have aryl ketones, we can use it for a Friedel-Crafts acylation. Basically, when you have a Lewis acid here, you can pick up any halogen and cross it out, and then the whole chunk will just go onto the benzene ring. Right here, you form acetophenone 95% with such a good yield. Now, we introduced you another molecule here to prepare aldehyde. It's called the Daz-Martin pyridinane. Now, pronounce it properly. I know that some people like to call this pyridinane, but actually the name comes from the molecule. You see here, this is the DMP in short. DMP. There's an iodine here. Iodine is taking a oxidation state of +5. So it's actually called periodinane. Alright? So this is a good oxidizing agent that could convert a primary alcohol into an aldehyde. Very stable. It won't go on to the carboxylic acid. It will stop here at the aldehyde. And of course, you can use another oxidizing agent, which is your dichromic 6. You can oxidize a secondary alcohol into the corresponding ketone. But nowadays we try not to use it in the lab because chromium stuff are rather toxic. And we recall that, right, when we have an ester, when you throw in a very strong reducing agent called lithium aluminium hydride, you can reduce it all the way to give the alcohol, in fact 2 alcohol. because you will slice it off and then after that you will reduce both to form the alcohol. Now to get an aldehyde from the reduction of an ester, we need to use something milder, not so strong, and we call this a dibar, or in some textbook they use dibal. Both are the same thing. It stands for diisobutyl aluminium hydride. This is the structure. Di means two. 2-isobutyl aluminium hydride. Very reactive, but milder than lithium aluminum hydride. Aldehyde can be oxidized easily into the carboxylic acid, but ketones are inert to oxidation. You can't oxidize ketones at all. Very stable compounds. So for the aldehyde, oxygen here from an oxidizing agent will go and insert between the CH bond of the aldehyde group and you get the carboxylic acid. And for the ketone, because there isn't any H at the particular bond site, so there's no reaction. Like I mentioned earlier, CrO3 is chromium 6 oxide, because the oxidation state of chromium is +6. We can call it the Jones reagents as well. Jones, Bridget, or doctor. Or we can also use potassium permanganate or hot nitric acid to oxidize these into the carboxylic acid. So here this is termed Jones reagent. You get hexanoic acid and a very good yield from hexanal. Now recall that, right, these two compounds under the carbonyl series, they can undergo nucleophilic addition because they have a polarized bond of CO double bond here. Delta plus is on the carbon, it is electrophilic. Basically it attracts nucleophile because it's slightly deficient in the electron density due to the polarization of the oxygen. So the hydride, a hydride equivalent, remember there's no free hydride. Hydride doesn't exist on its own, but it comes together with something else, it tags along. So you attack the carbon here and it goes in to form the alkoxide ion. When you protonate it using acid, you get back the alcohol. Remember this? Suprafacial and parafacial of the plane. Likewise, in the Grignard reagent, you can throw in, again it tags along something else, right? RMGX, it doesn't have any R minus on its own. So it attacks the carbon, which is electron deficient, and it goes in, you acidify it, you get the alcohol. So in general, when we throw in some nucleophile to a carbonyl compound, you should have some form of nucleophilic addition, right? Negatively charged nucleophiles, these are the ones hydroxide, carbanion, alkoxide, cyanide. Neutral ones, water, alcohol, ammonia, and amine. Now, two products can arise from the tetrahydroalkoxide ion intermediate. So nucleophile first go in, pi bond breaks goes up, O minus gets a charge. Next is this can be protonated and you get the alcohol. Or after doing that, it undergoes a spontaneous dehydration here to form a pi bond again back with the nucleophile. So remember, two possibilities. But you have to know which are the ones that can give that possibility, which is the one that gives this possibility. Now, aldehydes are more reactive than ketones in general because of electronic factors. R groups, we know that they are electron releasing, so they will donate electrons to the carbon that's electrophilic. But the thing is, for ketone, we have got both sides giving off electron density towards the carbon, so this carbon here doesn't feel so poor in terms of electrons, unlike the one in aldehyde. And we also know that for steric factor, aldehyde wins as well because H is so tiny it doesn't prevent the trajectory of the nucleophile from entering the site of reaction. Ketone is bulkier, big electron cloud, so the nucleophile may not be able to come in so easily. So in both cases, aldehyde wins. Normally in organic chemistry, we know that the two factors should counteract electronic and steric, but in this case, no exception. Aromatic aldehydes are less reactive than the aliphatic aldehydes. You should know this because we have a big ring here that blocks the way of the nucleophile, and by steric effect, it is less reactive. And for electron effect, it goes the same way, because you have some electron donating resonance effect of the aromatic ring that makes the carbonyl group less electrophilic. You see, I can push pi electrons out of the ring, and you see that now the O carries a negative charge. It means that the carbon next to it doesn't feel so electron deficient. That's why it doesn't attract the nucleophile so bad.